Good evening and welcome to prime factorization, one of the greatest topics in math of all time. Number one, first of all, I want you to pause this video and copy down this warm-up. I'm going to have you do this from time to time here, just to speed things up, and so the video looks less intimidating. But prime factorization means taking a number and breaking it down into the simplest possible factors. I prefer factor trees. I love factor trees because you can always get to the same place in multiple ways. Number one is the number 42. I factor tree that out. I know that 42 can come from 6 times 7. And if I break it down, I get 2 times 3 for the 6. 7 is done, so I'm going to circle every prime number, 7, 3, and 2. And I know that the prime factorization of 42 is 2 times 3 times 7. I want you to see how else I could get that. I'm going to go over here on the right and say 42 is made up of 21 and 2. 21 is 3 times 7, and if I circle all the endpoints of the trees that are prime factors, I have 2 times 3 times 7 as well. It is customary to list these in order, from smallest to biggest, and it's also customary to do something that we're going to see in this next one. So I'm going to erase these factor trees. You can keep them there and just kind of write in some blank space, but we're going to go with 56. 56, it can be a few things. We can say it is 8 times 7, which is probably the simplest one to break it down, and then to take 8 and break it down into 4 times 2, and watch, I'm going to circle the 7 and circle the 2 because those are prime. Those are dead ends. They can't be factored anymore, but 4 can break down into 2 and 2. And I have 2 times 2 times 2 times 7. I could write it like that, but it is more customary and better to write it as 2 to the third times 7. So we have a prime factorization for 42, we have one for 56. Number 3 is asking what is the greatest common factor between 42 and 56, the largest number that could divide each of them. Well, if I look at the prime factorizations of each of these, 2, 3, and 7, and 2 cubed times 7, I see that what they have in common, and that's really the question, what do they have in common? But what they have in common is a single 2, this 2, and a single 7. They have a 2 and a 7 in a common, which means that the greatest common factor should be 2 times 7. Which we say is 14. And in fact, 42 divided by 14 is 3, and 56 divided by 14 is 4. They both divide 14. Number 4, what are the positive prime factors of 48? Notice how I said positive. Every factor could be duplicated and be a negative. I want to hold on this word factor for a second. We're going to use that many times. We're going to say factor, noun. I'm going to do a very simple definition, something that is multiplied. Something that is multiplied. A factor implies multiplication, whereas a term or a monomial implies addition, subtraction. So it's important to keep in mind, what are the positive factors, things that multiply into 48? And notice I don't say prime factors, I just say any factors. Well, 1 is a factor. It's a positive number. And then 1, we could pair that with 48. 1 times 48 is 48. I'm going to kind of work my way from the outside in. 2 is a factor, and 48 divided by 2 is 24, so 2 and 24 are both factors. 3 is a factor. If we divide 48 divided by 3, we get 16. 4 is a factor. 48 divided by 4 is 12. 5 is not a factor, but 6 is a factor, 6, and paired with 8. And since 7 is not a factor, we have now listed them all. These are all the prime factors. Number 5 asks, what are the positive divisors of 48, things that divide 48 evenly? I'm going to let you think about that for just a second and give you the answer in 3, 2, 1. They're the same thing. It's another way to say exactly the same thing. Factors, divisors, they're just things that evenly divide. Just look at another way of looking at it. So number 6, we're going to kind of look at this from a few angles. And I have an x to the 4th over an x. And what I'm going to write out is I'm actually going to write the whole thing out. X times X times X times X over X. Then with number 7, oh I know, I'm just going to keep it here right now. No canceling yet. Number 7, it's a 3 times X times Y over, and 9 we're going to factor out into 3 times X times X times X times X times X 5 times. I want to see on your notes that you have done this, because this is crucial in understanding where we're going to go. Which means that with number 8, you are going to take the painstaking task of writing Y 10 times. It's okay, I'm already at 5, 6, 7, 8, 9, 10. With little dots in between. Over 8 more times. Let's make this a not cursive Y. 6, 7, 8. 10 Ys over 8 Ys. We are not going to cancel yet. We're going to do this proposition. The first property of quotients defines A, B, C, and D are real. We're going to say B and C, or sorry, B and D are not equal to 0. What we're going to say is AC divided by BD. That is the same thing as A over B times C over D. You may remember this as how to multiply fractions. A times C over B times D combines to become AC over BD. This is kind of the same thing as multiplying fractions, but what we're trying to treat this as is actually a little bit of a separation. I can take fractions like this up at number 6 that are already combined, and you don't have to write this down. I know you get annoyed when I move text around, but I can separate that into this. I can say that that is the same thing as X times X times X over 1 times X over X. I think everyone here knows what X divided by X is. That is 1. And that's the essence of what canceling really is. Another thing we want to kind of point out is that if I have BC over BD, that's the same thing as CD, provided, of course, that B is not equal to 0. You can never divide by 0. But that's the essence of what this is. I can cancel the B's not because they're the same, because I'm dividing the same number by itself. I want to put over here in this kind of white space under the property of quotients that there is no property that says this, B plus C over B plus D is equal to C over D. That is a big X. That is not true. In fact, we're going to emphasize that and put that in red. I cannot tell you the number of times that I'm going to talk to you guys this year about the fact that this move cannot happen. That is not true. You cannot cancel things that have pluses and minuses next to them. Those are deal breakers. What we're going to learn is that B plus C over B plus D are as different from each other as Reagan is from Gino. They're just very different people for a number of reasons. So those can't cancel, even if we add the same thing to both of them, even if we give them both. I'm thinking of a ton of things here that are probably not good to say, but if we give them both something, we still can't cancel. They're not the same thing. B plus C over B plus D is as different as 4 over 7. We can't cancel. So don't try that. But let's go back to what we can cancel. I'm going to go back to 6, 7, and 8. Clearly in 6, I meant for those to cancel. In fact, let's change colors so you don't think red is bad, unless you're colorblind. That is grouped together, and that could kind of multiply back out. But we're going to leave that here for now. I'm just going to try to make the point of what can we cancel. In number 7, we can divide 3 by 3, another x by an x, another x by an x, and then we'd be done. In number 9, 1, 2, 3, 4, 5, 6, 7, 8. 8 of them are gone. 2 of them are left in the numerator. So that's kind of the essence of this. Yes, I'm leaving those there for now. Let it go. We're not going to finish those problems. We're going to move on to something like number 9. I'm going to factor number 9 out completely. 32 factors into 16 and 2. 16 is 4 and 4, and 4 is 2 and 2, and another 4 is 2 and 2. 1, 2, 3, 4, and 5. 32 is 2 to the 5th power. X to the 5th power. Over 94, I'm going to do over here. 94 factors into 47 and 2. That's done. 47 is a prime number and 2 is a prime number. 47 times 2 and x to the 7th. Now, I'm going to be obnoxious again, like you love me to be, and write 2 times 2 times 2 times 2 times 2 5 times, then x times x times x times x times x 5 times. This is how I'm going to know that you did the notes. Over 47 times 2 times x times x times x times x times x times x times x. Trust me, you will not have to do that on your homework. We are now going to cancel what we have. I have a 2 on top and a 2 on the bottom. I have x here, x here, x here, x here, 3, 4, and 5 times. We are going to then remultiply whatever is left. I have 2 to the 4th power, which is 16. I don't have any x's left in the numerator. I have 47 in the denominator, and I have 2 x's left in the denominator, x to the 2nd. If you compare your answer with the original problem, you can start to see how this is going to work. So let's kind of move ahead with this. Rule of exponents for division. If a is real and a is not equal to 0, and we have these little m and n are positive, then a to the m over a to the n equals a to the m minus n. This rule is what I affectionately refer to as rule number 2, and I'll show you the 3 rules down here at the bottom. But this rule I just wrote here is true if m is greater than n. If m is the bigger number. Actually, it's true all the time. We just write it like that if it's true. Typically, if we have a to the n over a to the m, then we're going to say that that's the same thing as 1 over a to the m minus n. And that's going to hold true also if m is greater than n. So if the bigger one's on top, we're going to subtract and keep it on the top. If the bigger one's on bottom, we're going to subtract and keep it on the bottom. But the bottom line here is these 3 rules that are crucial to understanding this chapter. Rule 1. Multiply the same base. Add the exponents. Rule 2, which we just did up above. Divide same base. That little a was the base. Divide same base. Subtract exponents. And rule 3, which we've already done. That's the power of powers. Raise power to another power, and you multiply the exponents. We've done rule 1, we've done rule 3, we've now just done rule 2. We have 3 rules of exponents, and let's do some problems. So, number 10. The way I do this is I look to see what's on top and what's on bottom, and I'm going to look at the m's first and the n's second, not together. What I have here is I have m to the 7th over m. That's going to leave me, I'm going to start a new fraction bar, and that's going to leave me with m to the 7 minus 1, which is 6. Why minus 1? Or why is it minus 1? Because the m in the denominator has an exponent of 1. Now let's direct our attention to the n's. You have an n to the 6th and an n squared, and the bigger one's in the denominator. 6 minus 2 is 4, and so we're left with an n to the 4th, and this is considered simplified. Let's go to the 11, or number 11. We have to yep, those are not common bases. So we're going to have to simplify this first before we move on. This is going to be 5 to the 3rd, a to the 6th, over 5 to the 2nd, a to the 6th. It is not necessary to write out 5 to the 3rd and 5 to the 2nd. Your a to the 6's are going to cancel because they divide to become 1. And your 5 to the 3rd over 5 to the 2nd is the same thing as 5 to the 3 minus 2, or 5 to the 1, or 5. Number 12, the negative is part of the coefficient. That's a negative 1. Kick it off to the side, it's going to stick around. 7 over 28 can cancel. They have a common factor of 7. That's going to be 1 over 4. So I'm going to write a 1/4 here and keep this thing going. Let's check out the a's. We have a squared on top and a on the bottom. It's going to cancel to give us an a on the top. B to the third over b is going to cancel to give us a b to the second. And the c in the denominator is going to stay because there's no c to cancel with. Now, it is not necessary to write the 1 anymore, so I can leave that as negative. We'll keep the negative here. AB squared over 4c. Made the fraction bar too long, but you can get over that. Number 13, we got two negatives. Funny thing about two negatives being a positive. So those are gone. 52 and 39, let's think about what they have in common. This is a little bit tricky, but they both divide by 13. 52 is 13 divided by 4, and 39 is 13 divided by 3, or 13 times 3. So we get 4 and 3. Let's check the x's. X squared over x cubed is an x in the denominator. Y to the 6th over y. Cancel one of the y's and we get a y to the 5th. Z to the 2nd over z to the 3rd, and we have a z in the denominator. And that's done. Isn't this fun? Number 14. I actually really mean that, and that's the scary thing. Number 14, we have 3 to the 4th over 3 squared. Don't raise them yet. Let's just cancel the exponents by subtracting the exponents. We have a 3 squared on top. A to the 8th over a to the 5th is a to the 3rd. And b over b cubed leaves us with a b to the 2nd in the denominator. How do I know it's in the denominator? Well, because a b cubed is bigger than a b, and the bigger one will stick around where it was before. We're going to simplify this now to 9a to the 3rd over b to the 2nd. 15. Let's not get tricky about what's the base. That is really a negative 1 to the 9th, x to the 9th, y to the 9th, over x, y to the 9th. So negative 1 to the 9th is negative 1. That's going to stick around as a negative. X to the 9th over x is x to the 8th, and the y to the 9ths cancel. Negative x to the 8th. Number 16, we're going to follow order of operations and raise the 3 squared, m squared, n squared, over. And I'm going to stick dots in between these because I really want you to see the separation of this. It's kind of tricky with what's happening up above. This is really 3 times m times n to the 3rd. That third power in the denominator is only part of that n, part of nothing else. So 3's cancel, 3 squared and 3, and we get a 3 in the numerator. M's cancel, and we're leaving us an m, and n's leave us an n in the denominator. 3m over n. Number 17, we're actually multiplying fractions, which doesn't mean anything. We can actually extend the fraction bar, get rid of that dot, and put it in between the numerator and denominator. It's all the same stuff. 17, we go negative 2 in the numerator. X squared times an 8. Y to the 5th over. Then I'm going to raise the 4 squared. X to the 6th. Still have a times 20 and a y cubed. Now, why didn't I multiply the 8 and the 2? I could have. I certainly could have. And it might have made sense to, but we got to just kind of look at this whole thing right now. 2 times 8 is 16. 4 squared is also 16. 16 over 16 is 1. Let's just put a slash here, and a slash there, because that's all going to cancel each other out. The 16s are gone. So I'm going to start building this again. The negative sticks around, so we have a negative. X squared over x to the 6th is going to leave us an x to the 6th in the denominator. We also have a 20 in the denominator that we're going to stick out in the front, but it's still part of the denominator. And then we have a y squared on top. I'm just going to rewrite it to look a little cleaner. Negative y squared over 20 x to the 4th. 18. 18's tricky. We have a variable in the exponent. We have a base with three parts to it. So I go negative 1 to the 2n plus 1, x to the 2n plus 1, y to the 2n plus 1, over x to the 2n, y to the n plus 1. Let's examine all of these differently. Let's start with the negative 1. I'm going to argue that 2n plus 1 is an odd number. 2 times n is an even number. Whatever n is, 2 times n will be an even number, and then plus 1 will be an odd number. Negative 1 raised to an odd number is negative 1. So that's negative. Let's go to the x. What is bigger, 2n plus 1 or 2n? I think you know 2n plus 1 is bigger. When you raise, you subtract exponents. We're going to go x to the 2n plus 1 minus 2n. Y, what is bigger, 2n plus 1 or n plus 1? I think everyone agreed 2n plus 1 is bigger. So the y's we're going to subtract 2n plus 1 minus parentheses n plus 1. Okay, let's clean that up. We have negative x. 2n's cancel, 2n minus 2n, leaving us plus 1, which is just a 1. The y's, we have y to the 2n plus 1 minus n minus 1. Distributed the negative. Some of you guys didn't do that on the quiz. You didn't distribute the negative first. So let's just take a step, and now I'm left with negative x, y. The 2n minus n is n. Negative 1 is negative 2. And that's what we're left with. Number 19. I kind of used some of the space in 19, so I'm going to separate here. Let's cancel. This is another way to kind of look at this. I'm going to cancel just the coefficients. I'm going to go 5 and 25 gives us a 5. 12 and 36 gives us a 1 and 3. Now I'm going to start to write these a little bit more grouped. Let's go negative 3 and a 5, because those are kind of carrying from the previous, canceling. And then let's look at the x's. I have x to the 7th, y to the 5th on the top. I added the exponents in the numerator. Then I have x to the 6th, y to the 3rd in the denominator. I carried those across the denominator. There we go, that's better. Now I'm going to cancel within the fraction. So we still have negative 3/5. But the x's are going to cancel, leaving us a single x on top. And the y's are going to cancel, leaving us a y squared on the top. And that's okay. Okay, number 20. We've got 3's to cancel, 1 and 9. 4 and 12 to cancel, 1 and 3. Then we have another 3 to cancel, 1 and 3. Oops. So I'm left with the 1/3. But let's extend the fraction bar. Let's look across the numerator. When I'm looking across the numerator, I'm looking this way. I'm just looking for x's and looking for y's. We have negative 1, x to the 3rd, y. And then I have an x, y to the 3rd in the denominator. Let's cancel. I get, let's see, we don't need to write the 1. We have an x squared. The y's are going to leave us a y in the denominator. There's still the 3. And when the y's cancel, we have a y squared. Done. Number 21 is a massive canceling. Let's start with the constants, or the coefficients. 4 and 8 are 1 and 2. 2 and 6 are 1 and 3. 3 and 3 are 1 and 1. Let's put a negative 1 to remember that that was negative. We got 2 negatives, so I'm going to put a positive, and get rid of those. Then I still have a 2 and 24, so 1 and 12. Clean all that up, and that's a 12 in the numerator and nothing in the denominator. Let's look at the a's. I'm just going to combine all the a's in the numerator again. A to the 3rd, a and a gives us a to the 5th. B is b to the 3rd. Then we have a to the 4th and b to the 3rd. Okay, write it one more time. Got a 12, a, and the b's cancel. No fraction bar was needed. It's just 12a. Okay, these get a little bit more complicated now. Our base is w plus x. So all I'm going to do is, you cannot distribute that and make it w to the 4th plus x to the 4th. The w plus x is your base. That won't change. What I have to do is I have to treat this like the same thing as, I'm trying to change colors here, treat this like it's the same thing as x to the 4th over x to the 5th. That would just be 1 over x. So this is 1 over w plus x, because w plus x is the group. The 5 and the 4 subtracted, that's it. 23, if I look at what's in common, these are the same base, and so that leaves me an r minus s in the numerator, really to the first power, because of the 2 minus the first power here, over r plus s in the denominator. It really looks like those can cancel, but they can't. I actually put the parentheses around there so you'd see them, that they can't cancel. Really, you're probably supposed to write it like this because the grouping symbols are implied, plus S. Well, that's it.